All right. Let's do Pangea, the basics of continental movement and plate tectonics. We're going to go fast because if you look, there's 30 slides. All right, Pangea, first proposed in 1920 by Wegener. Remember, it's not Wegener, it's Beckner with a B. It is from the Greek word, which means all world. It was viewed as one supercontinent, meaning that they were mostly connected. There were pieces like lakes and stuff in it, but it was continuous collection. The science that supports this is great. It's not just one piece of information, it's geographical information that supports this. It's paleontological information that reinforces this, and it's geological evidence that supports this. So if you look at the picture on the very far right, here, there's this C shape that it has. This blue line here is the equator. And if you look, there's two continents that really haven't moved through time. I mean, they've wiggled around a little bit, but they haven't veered too far off of the equator, and that would be South America and Africa. So those two continents will become a focal point for a lot of our discussion. So Wegener, let's look at him. His lifespan was from the 1880 to 1930, so he lived quite a long time. In 1920, that's when he published and got support for his writing about Pangea. And so in school, there's a story in school that he was in class and his teacher was saying that this is how the continents have always been. They've always been in this location. And he said, and there's a quote there, it says, "Doesn't the east coast of South America fit exactly against the west coast of Africa? As if they had once been joined." So he said this to his teacher, but he wrote it and published it in 1910. So within 10 years of his first publishing this and then him getting support. So it took 10 years for him to get information to support this. You would probably find it funny that he don't do this. Do not do this. He went and got, to prove to his teacher that they fit, he got books from the library and cut out South America and cut out Africa and put them together. And they do fit. There's not a perfect fit. If you look over here on the right, there's some space here in between where they don't perfectly fit. But those coastlines have changed over time. So who's to say they didn't at that point? Wegener found papers that said that Africa and South America had once been connected by a land bridge, which then sunk into the sea. So that finding kind of helped spur his thinking and his logical sequencing of events. That he said, okay, if there was a land bridge, then that could argue why some of the things we found are together. So if you look in this last bubble, it says he wrote in his paper that he found evidence from fossils that matched in both areas, that lived at the same time. And these are animals that are huge, very cumbersome, weighed an intense amount of weight, like they weighed tons and tons of kilograms, so they couldn't have swam. Their bones were too dense, they would have sunk. So how did they get across if it weren't either for this land bridge or them being connected at some point? So this is more of Wegener. In 1912, in Frankfurt, Germany, he introduced his radical theory, and he was basically laughed out of the room. People were just like, this is totally inconceivable. They dismissed his concept of a land bridge. They dismissed his concept of the drifting continents and the widening sea. He pointed to the continents, that the less dense rock, granite, which we've studied, and the volcanic basalt is what makes up the ocean floor. So if they moved, if granite and basalt were put next to each other, they don't stay at the same level. They move because of their densities. He proposed that the less dense granite would have floated kind of like an iceberg in the water. Like, it doesn't sink all the way down. You would still see pieces of it. And he noted that when South America and Africa were together, either through a land bridge or their plates being in that way, that their mountain ranges were the same and they're the same age. And then he brought up coal because, people listen to where money, and money is in coal because that's an energy form. He said that their coal deposits were at the same depth and they were at the same age. So in 1922, this is after he's published it and kind of been giggled at a little bit, he starts finding geological evidence that adds to his basis. So he was just looking at fossils. So now he's looking more not just at fossils, but at the geological, the rocks within it. And he said, looking at those rocks, that it would have been about 200 million years ago that the Pangea would have started to break up. So that's when the continents started to move to their positions. The geologists started then to start calling this plate tectonics, which just means the movement of the plates, and started to take his word a little more and not quite so, not release it so flippantly or just disregard it so fast. Make sure I don't have anything in here. And I don't, which is awesome. So we're going to look at our timeline at the end of class, or at the end of this, you'll have to get the next video that talks about timelines. And this Paleozoic, Mesozoic, and Cenozoic. The Mesozoic, this grouping here, is the dinosaurs. So from Pangea, we have birth of some dinosaurs, and then the Mesozoic is where most of the dinosaurs are. So if you look, South America and Africa are connected in this grouping called Gondwana. And as it moved, some of these animals, the dinosaurs, were able to just walk across. So if I look to when it died, the Mesozoic era ended, which would be that giant meteor that hit, they're in close to their current positions. So these pieces of evidence, the rock and how they moved, we did a lab where we did a flip book, so use that as your reference. So then another guy that was involved was Harry H. Hess, or if you just call him Hess, then that's specific enough. He looked at the theories of seafloor spreading and suggested that the convection currents were what was moving our planet, our plates. And so when he started using Wegener's information, by the 60s, Wegener's ideas were pretty well accepted within the science community, but the rest of the general community was still very hesitant about accepting this information. But Hess used his information to further the idea that the seafloor would be spreading, and if it were spreading, then he should be able to find it. When he did, it's the Mid-Atlantic Ridge. If you look at this middle box, in 1960, he discovered what he called the Great Global Rift, which runs in the middle of the Atlantic Ocean, and most of us just call this the Mid-Atlantic Ridge. But this helped support his concept of convection currents. So he was really the first guy to suggest the idea that convection currents were at the basis of movement. Drummond Matthews, he's the one, he worked with Hess a little bit to create detailed surveys or maps of the Indian Ocean and show the magnetic polarization of the rocks. And so I think I put it on here. Boop, boop. Yep, I did. So he worked with another guy, the next guy on the slide, Vine, and said that he would take magnetic readings of these bands or pieces of rock. So here's, in this picture up here at the top, this is where the ocean is splitting. So I have, if it were moving, I would have groups of positive banding, positive negative band, or negative banding together, and then another group of positive bands together. He also argued that the further away from the origin of the lava escaping, the older the rock would be. So this is a really crude drawing. So as the magma comes up through the opening and the land is moving away in a divergent boundary, grouping 1 would be much older than grouping 2. So looking at the next slide, Fred Vine was his counterpart, and Fred Vine was a cartographer, which means he makes maps, and they worked together to devise this polarity. And they used something called sonar, which is echoes and pulses of energy. So they saw that if this is the ocean ridge, that each of these band color changes would mean a polarity change. So if the black is positive, then the white would be negative in like a positive, negative, like a magnet. So with their information, they were able to help support the plate moving. So then this is 3 key facts. We're going to go really quick because this should be review. So we have 3 layers. The 3 big main ones that we talked about are the crust, the mantle, and the core. Each have a different job and each have different densities, which is what makes them different. The magnetic field generates within the liquid mantle, and if you look at the picture, it kind of gives us a force field that protects us against solar wind. It protects us from stuff flying and trying to kill us, like meteorites. The lithosphere is the crust and part of the upper mantle. It's extremely thin, and it floats on the stuff below it, which would be the asthenosphere. The asthenosphere is just below the lithosphere, and it's kind of like Jello that you left in the refrigerator too long. It's kind of squishy, but it's kind of hard at the same time. The asthenosphere is the upper part of the mantle, and it's where the convection currents are. So the crust, 10 miles in its depth of loose material underneath it. It varies in thickness depending on whether it's crust or ocean. The crust is almost 3 times thicker than the ocean. The 2 types, basalt is under the ocean, and if you can remember salt of basalt, and the salt is in the ocean. The basalt is more dense than the granite. Granite is what we use on our countertops, and it floats on top. The mantle extends fairly deep down. It's the biggest layer of our planet, and the mantle is more like liquid, the Jello that you would want to eat. It's more squishy. It's 85% of our total mass and weight of our planet. The outer core is mostly made of iron and nickel, and it's superheated liquid lava. So the outer core is liquid. That's the biggest part that we need to remember. The inner core is that solid ball. This is, again, mostly iron and nickel, and it is completely solid, and it's what helps give us heat. It's also what helps drive us. So I'm going to stop it here. This will be video 1 in plate tectonics, and it'll pick up here for video 2. So there you go. So catch the next video.